Welcome to the Deep Dive. Today, we're tackling a really big one, antimicrobial resistance, AMR. It's a major global health threat. Our mission, to unpack all the ways we detect it, from the old school lab tests to the super high-tech stuff, and figure out what it all means for you.
It's definitely urgent. AMR is a serious problem. Sources show it was linked to maybe 1.27 million deaths globally back in 2019, and the costs to healthcare are huge. So finding fast, accurate, and importantly, affordable ways to detect it is absolutely critical for patient safety.
Okay, let's start at the beginning then. The classic methods, what are those?
Right, the traditional approach. We're talking microbiological cultures, basically growing the bacteria in the lab and then testing different antibiotics against it. Think disc diffusion or MIC tests, minimum inhibitory concentration.
So you see if the antibiotic actually stops the bacteria from growing. Sounds fundamental.
It is. These are often the baseline, relatively inexpensive too.
But there's a catch, right? I mean, growing bacteria, that takes time.
Exactly, that's the main drawback. These methods are quite labor-intensive and they're slow. You're typically waiting 18, sometimes up to 36 hours, maybe even longer, for results.
Wow, 18 to 36 hours.
Right.
That's a huge delay when someone's sick. It must really affect how doctors treat patients.
It absolutely does. That delay often means starting with broad-spectrum antibiotics while you wait, which isn't ideal. It can impact patient outcomes, definitely.
Okay, so the next step was trying to speed that up. Automation.
Precisely. That bottleneck led to automated systems, things like the Vitek 2 or Microscan Walkaway, you might have heard of them. They're FDA approved. They automate parts of that susceptibility testing process. So you get results faster, usually within maybe 2 to 24 hours.
Much better, but still based on growing the bacteria first.
Often, yes. Many still need that initial culture step, so there's still some waiting involved before the machine even starts its part.
Right. So what if we could skip the growing part? That leads us to the molecular techniques, yeah, like PCR.
Exactly. Nucleic acid amplification tests, or NAPETs, including PCR. These are revolutionary because they look for specific resistance genes. Think MECA for MRSA or BLASH-HV for resistance to certain common antibiotics. And they can often use samples directly without purification. Very fast.
Okay, fast sounds great. But finding a gene, does that automatically mean the bacteria is resistant right now? And what about knowing how much antibiotic to use, that MIC value you mentioned?
That's a really important distinction. NITEs detect the genetic potential for resistance. It doesn't always guarantee the bacteria is actually expressing that resistance, what we call phenotypic resistance. And you're right, most NITEs don't give you an MIC value. That tells the doctor the level of resistance, which helps guide dosing. Without it, treatment is less precise.
And the cost? Are these tests expensive?
They can be, yeah. Commercial tests might run, say, $100 to $250 per sample, so access can be an issue.
Okay, so PCR is fast for specific genes, but maybe not the whole story. What about seeing the entire genetic picture? That's where next-gen sequencing comes in.
Exactly. Next-generation sequencing, NGS, especially whole genome sequencing or WGS, this gives you a complete blueprint of the organism's DNA. You can spot complex resistance patterns, track outbreaks. It's incredibly powerful for infection control.
But I'm guessing it's not simple or cheap either.
Correct. The cost is still relatively high, and interpreting that huge amount of data requires specialized bioinformatics expertise. So it's powerful, but challenging to implement everywhere.
All right, another tool you hear about is MALDI-TOF. What's that about? Sounds like something from science fiction.
Maybe a little. MALDI-TOF mass spectrometry. Think of it as creating a unique protein fingerprint for the bacteria. It's incredibly fast for identifying the bacteria itself. And now it's also being used to detect certain resistance markers, like the MECA protein for MRSA or KPC enzymes, which cause really dangerous resistance. Results can come in just a couple of hours.
2 to 3 hours. That's a massive improvement. And cost.
Relatively affordable per sample once you have the machine. It's really changing rapid diagnostics in many labs.
Okay, so we've gone from days to hours. What's next? What does the future hold?
Some really exciting things are on the horizon. CRISPR-Cas technology, for example. People are developing tests using CRISPR to directly find and snip out resistance genes. Super specific, super sensitive. Some promise results in under 90 minutes. Huge potential for personalized medicine.
Wow, CRISPR for diagnostics.
What else? Lab-on-a-chip devices. These are tiny microfluidic systems that can run tests, even complex ones like MICs using tiny sample volumes. They can be automated, portable. Imagine getting rapid MIC results right at the bedside or in a local clinic. That tackles the delay head-on.
That sounds incredibly useful. Anything else simple and fast?
Yes, lateral flow immunoassays, LFIAs. Think like a pregnancy test, but for specific resistance markers like KPC or OXA48 enzymes, they're simple, fast, cheap. Really valuable for quick screening, especially in places with fewer resources.
So we've got this whole arsenal, from slow cultures to rapid gene finders to future tech. What's the big takeaway for our listeners? For you?
I think the main thing is that there's no single perfect test. Each one has its strengths, its weaknesses, its place. The goal is to use them smartly, combine them perhaps, to get the right information quickly. This helps doctors make better decisions, stop resistant bugs from spreading, and ultimately keep patients safer. Better, faster information leads to better care.
Right. It sounds like the future isn't about replacing everything, but integrating these different tools smartly. So here's something to think about. How do we strike that perfect balance between speed, accuracy, access, and cost to get this life-saving information where it's needed most? What advancements stand out most to you in this fight against AMR? Thanks for joining us on The Deep Dive.